Hey everybody, welcome back to another round of physics, and yeah, let's get going. We have discussed the idea of forces that magnetic fields exert on moving charges, namely that the force is given by the charge times the velocity of the charge crossed into the external magnetic field. Or conversely, we can think about this. If we look at this first term, it is a Coulomb meter per second. You could conceptually think about reorganizing that into something like a Coulomb per second times a meter. And that is where you kind of get at the second equivalent statement, namely that the force acting on a charge carrying wire is given by I, and I'll put in here dl cross B. So the charge per second times the distance. Now, of course, technically speaking, I should put a df here, since we have an infinitesimal length of wire, and that contributes an infinitesimal force acting on the wire. But, if you know the length of the wire, or if the magnetic field is constant over the entire length, then you can replace this with just L and then be on your merry way. So now, what we have not talked about yet is an equation describing how the magnetic field is actually generated. And so that is the topic for this lecture, namely the law of Biot-Savart. So the law of Biot-Savart, let me go ahead and give it to you in equation form. Now, this is empirical relationship, so I don't know if there was any underlying theory that guided Biot-Savart to actually to derive this equation. But what he found out was that the magnetic field is given by mu naught over 4 pi. Excuse me, this is a vector quantity. And then up here, he had something like I dl cross r hat, all divided by, and here I'll be very careful. I'll go ahead and put this, the relative position vector squared. There we go. Okay. Now let's go ahead and walk through this. And this is the equivalent relationship for magnetic fields. So if you want, Biot-Savart is analogous to Coulomb's law. Coulomb's law. Okay. Right? The equation that tells us the electric field generated by a particle is 1 over 4 pi epsilon naught q over squared r hat. Right? That is the kind of the idea that we're going for here. Okay. Now, please bear in mind is that this current and this length of wire, so IDL here, those are objects that are in the surroundings. So it is very easy to confuse the current carrying wire in the surroundings with the current carrying wire that you are considering as a system. If I go back up to this forces thing, this, what I'm underlining in blue, would be the current carrying wire in the system. And then what I have in red in the law of Biot-Savart is the current carrying wire that's in the surroundings. Okay? So that's the first thing, is to just be careful and be very methodical, right? This is no different than when we talked about, again, the Coulomb force, and we said, well, that's given by Q times E. This E was in the surroundings. That was the kind of the influence of the surroundings all packaged into a vector field. And then the Q that we use, that would be the charge of the system, the object that we want to see the interactions with. Okay. So the same thing happens when we're dealing with these forces due to magnetic fields. Okay. So a lot of those, that's also partially why we end up doing electric fields first, is because now that we've had some familiarity with how we go about calculating the electric fields, how we go about using the electric field to determine forces, then it should feel somewhat familiar as we go into magnetic fields. Okay. Now you will notice some similarities even with Coulomb's law. So in Coulomb's law, we had that 1 over 4 pi epsilon naught, or sometimes in class, we ended up using just the Coulomb constant K. Okay. Similarly, in the law of Biot-Savart, you notice that we have a 4 pi, but also we have this, instead of epsilon naught, we have a mu naught. Okay. Now, epsilon naught, as you are well familiar, that is the permittivity of free space. Free space. And as I tried to convey to you, it gives you a sense of how the electric field, for lack of a better term, polarizes vacuum, empty space. Or maybe a little bit more abstract, it is a generalization of how the electric field propagates through vacuum. And as we saw when we put dielectrics into our capacitors, we knew that dielectrics, instead of using epsilon naught, we ended up using epsilon. And that would give us an idea about how the dielectric polarizes, thereby creating an induced electric field and decreasing the potential drop across the capacitor. Okay. Mu naught serves the exact same purpose with a slight tweak. First of all, we call it the permeability of free space. And the only way that I remember it, this is what my physics professor told me, goodness knows how long ago, was that he said, you have ability, right? So you, the Greek letter mu looks like you. So he said, you have ability. Okay. So that's the U goes with ability. And like epsilon naught, mu naught is conveying how magnetic fields propagate through empty space. You say, well, wait, Greg, what happens if I have a material? If I want to know how magnetic fields affect a material, you probably already know the answer. Yeah, instead of using mu naught, you would just use mu. So the permeability of the material. Okay. Now, truth be told, you will get a larger variation in permittivities than permeabilities. Generally, the permeabilities of materials are very close to that of vacuum, whereas the permittivity of materials tends to be a large range. And we'll use that idea when we come and start talking about propagation of light. Okay, so put that on the sideline, but that is tends to be the case, is that the permeabilities tend to be very close to one another. To give you a sense, mu naught is given by, it's equal to 4 pi times 10 to the negative 7th. And now I have to think about the units here. Let's see, this would be a Tesla meter per amp. So if you want to know the value of mu naught, there you go. Of course, that's also given in the back of the book, but it's always, again, you get tired of looking it up eventually, that you end up memorizing it. Good? Yeah, good. Now, other things. You notice, again, so we have a constant out front, just like when we were dealing with the electric field, just a different value for the constant. Second of all, let's go ahead and focus in right here. So just like when we were dealing with the electric fields, we have this r squared in the denominator, and that r squared is the relative position vector. Right? And it points from the source current to the field point. Okay? So just like how the R in Coulomb's law pointed from the source charge to the field point, this is the same R, only it's a current, a source current to the field point. Okay? Now in the numerator, you notice that we do have slight differences. First of all, currents require some sort of wire to travel along. And so inherently, we're going to have to do some sort of integration if we wish to find the total magnetic field due to a current carrying wire. Or some people will say, instead of a charge distribution, we will sometimes refer to it as a current distribution. So that's one difference, is that inherently you have to start worrying about the integration process. The second issue is that you notice that in the numerator, we now have a cross product. So for Coulomb's law, it was just simply calculating out the unit vector, and that had to be the direction of the electric field. For the magnetic field, we have an extra twist that once we calculate out the unit vector, we have to do a cross product in order to figure out what the value of the magnetic field is. Now, if that doesn't ring a bell, okay, if you don't remember that, go back, watch the cross product videos. Okay, I'll make sure that those are posted so that you can get a refresher on how to actually calculate out the cross product. So that is the big differences between the law of Biot-Savart and Coulomb's law. Now, the last thing I will point out, I've already mentioned it, is that technically we have to do an integration here. Okay? So first of all, when we do a cross product, we have three ways of multiplying vectors, right? You can multiply by a scalar, you can multiply by another vector to get a scalar, and you can multiply by another vector to get another vector. This is the third type. In other words, when we do this vector multiplication, we end up with a third vector, I'll call it vector C for right now, which is perpendicular to the original vectors that we were using. Okay. So C will be perpendicular to the direction that the wire is oriented, and C will be perpendicular to the relative position vector. Okay. Now you say, well, how do you do this integration process? Because now you will have to do an integral to find the entire magnetic field. And how I would say this is do it like we've been treating all the rest of the vectors, right? If you go back and think about when we first ran into vectors with, say, something like projectile motion, what did we do? We break it into components. Or we go to Newton's laws, we break it into components. We go to momentum, we break it into components. Here, the same thing happens, okay? If you want to figure out this integral, what you can do is say, well, the x component simply must be the, for lack of a better term, what I'm going to do here is I'll call it I dl cross r hat. I'll say the x component of that cross product. Okay. You would just do the integral of the x component. Or if you wanted the y component of b, then you'll integrate whatever the y component of this cross product ends up being, et cetera, et cetera, et cetera. Okay. So you don't have to do anything fancy. What this simply means is that you have to do 3 integrations rather than 1. Right? The fact that you have a vector means that you have to do the x component integration, you have to do an integration to find the y component, you have to do an integration to find the z component. Okay. I will make a couple of extra notes here. One of them I realized that I just mentioned. It's very odd to have dl here. What we mean by dl is the direction that the current is running in the wire. Okay. So you can imagine for a second, if I get a coordinate system, I'll call it x, I'll call this y, and I'll call this z. We'll say it's a z day here. And if I have a wire, say, running this way, and the current is going that, we'll call it IDL that way. Okay. Here, DL is simply parallel to negative z hat. Okay. So you have to know which way the current is running in the wire, and based on your coordinate system, arbitrarily chosen, you should be able to express DL in terms of your coordinate system. Okay. Okay, so while we're at that, I guess I have a video. I'm going to splice in a video that I did finding the magnetic field due to a infinite current carrying wire. So let's start off with just a simple wire, a current carrying wire, and for argument, we'll make it a length of 2L. So let's assume for a moment we have a current carrying wire. We'll set I in this direction. We'll go ahead and give it a length of 2L. So we'll say that it goes a length of 2L. And we'll go ahead and make, since we have the ability to do this, with power comes great responsibility. Let's go ahead and I'll set it symmetric on my XY plane. Okay. So we'll do it like that. Okay. Of course, if X is to the right and Y is up, that means that Z is going to be out of the board here. Okay, so we have that. And oh yes, we should probably set up a field point for ourselves. We'll go ahead right now, for simplicity, we'll set it on the Y-axis. Start off with that. We could always offset it and then go at it later. See how that works. We'll say that it's a distance. We'll just call this a distance Y up here. Now, as some review, we've already discussed this once in lecture, but let's go ahead and review this. We should probably go through and just set up the problem. And so the idea would be is that I want some little chunk of wire, say this small chunk right here. Goodness knows I always insist on yellow instead of orange. So let's take a look at, say, this little chunk right here. And we should first talk about, or first write down the expression getting the relative position vector between this chunk that I've indicated, this little piece of the wire, which we refer to as DL, and that field point. So we need the position of the source. We go ahead and don't forget, since we're going to integrate from negative L to L, and I've aligned my source with the x-axis, the most general way to express the location of that little piece would just be using the variable x. And then we'll simply use the limits of integration to sweep out the ranges for the sources. Okay, well, it's not by accident. We chose the wire to lie on the x-axis. That makes our lives easy. Okay, so the other two are 0. Of course, now we need the field point. And again, by drawing our axes in a nice position, we can go ahead and write this down pretty quickly. Okay. Now we need the relative position vector. The relative position vector between the field point and the source. Well, that's, again, this is review, so I assume that you're working through this. That's the field point minus the source, right? You could think of this as final minus initial would be another way of thinking of it. And so we have x, comma, negative y, comma, 0. Well, now that we have the relative position vector, we can find the magnitude of the relative position vector. And how we find the magnitude is that we take the square of each of the components and then square root it. The Pythagorean theorem is one way to think about it. I'll also say a different way to think about it is that you're doing a dot product and then taking the square root, just in case you ever find that useful. So, okay, so same thing. It's the Pythagorean theorem. So we end up with something that says x squared plus y squared square rooted. Which means now that we have the relative position vector and the magnitude of the relative position vector, we're in a situation where we can now write the unit vector, namely the vector divided by its magnitude. So we go ahead and do that. We have something that says x comma negative y comma 0, all divided by x squared plus y squared to the 1/2. So we've got our setup. We've now set up for both the magnitude and the r hat vector. Okay. So that's good to go. Okay. Now, what I would recommend is the next thing that we should think about is performing this cross product. Now that we have, you could say, hey, now that we have the relative position vector, we could think about the cross product. Okay. So let's go ahead and do that. So we would like to evaluate dl crossed into r hat, or if you would prefer, you could think of this as saying dl crossed into the r vector, the relative position vector, and then taking that final result and dividing by the magnitude. Either one is fine. It'll get you to the same result. The only reason that I mentioned this second expression is that sometimes it just means that it's easier in the sense of less writing. Okay. Either one will get you to the right spot. Okay. I'm going to go ahead and do this second piece. Now, we haven't come up with an expression for dl yet, so we should do that. And we recall that dl, because of our choice of axes and the direction of the current, dl runs in the x direction. So I'll go ahead now, and instead of having this as an infinitesimal length and being a vector, I'll go ahead and express it as a small step in the x direction, 0, 0. Okay. Keeping in mind our relative position vector was x comma negative y comma 0. Excuse me, I think I have my signs backwards here. Hey, you caught that, right? I realize that now. For some reason, I have put I don't know how to subtract anymore. There we go. Order's been restored. So go ahead. Don't forget to change that. So, excuse me. It should be this. My brain has left me. Not enough coffee. So let's go ahead and perform the cross product. The dl cross r. You probably already see where this is going pretty quickly. Let's go ahead. X hat, y hat, z hat. We have dx, 0 and 0. We have negative x, y, and 0. So I'll go ahead. We'll do the first one. We have x hat times 0 times 0 plus y hat times 0 times negative x plus z hat times dx times y. And then we got to go and do the minuses. Minus y times 0 x hat minus 0 dx y hat. And then we have minus a minus x 0 z hat. And we say, oh, goody, goody. Right? 0, 0, 0, 0, 0. We get a bunch of zeros in there. And what we get at the end of the day is y dx in the z hat direction. Now that shouldn't be a surprise, right? If we go back and look, we could also have applied our right-hand rule to find that answer. current's flowing to the right, the positive x direction. My field point is in the positive y direction, so I have to turn my palm upwards. And it's directly over the wire, okay, which means that my magnetic field's out of the board. Of course, if you could keep doing this, you say, well, what happens if my field point's beneath the wire? Then you'll find that the magnetic field is into the board. Or how about if if you're the wire right now and the field point's out here, okay? The current's running that way to the right, and the field point is out of the screen. You'll notice that the magnetic field will run downwards, down. Okay. The shortcut would be is that the magnetic field at any point around a current carrying wire, okay, it will actually be going around like this. It'll kind of loop around, curl. The official term is curl around the wire. And you can get an idea of that if the shortcut. So right-hand rule, we've been practicing that with cross products. The shortcut to the right-hand rule in a situation like this is grab the wire with your right hand, with your thumb pointing the direction of the current. So imagine you take that wire and you grab it with your thumb in the direction of the current. Your fingers, as you curl your hand around that wire, will give you the direction of the magnetic field. So you can think of that magnetic field as curling around the wire. We'll leave it at that. Okay. So algebraically, we've shown that the magnetic field is only in the z direction at a location directly above the wire. So now we've shown that for a field point directly above the wire, okay, on the y-axis, if you will, we've shown that the magnetic field is only in the z direction. So let's go ahead and now plug everything that we have into the law of Biot-Savart. So the magnetic field, due to an infinitesimally small piece of that current carrying wire, is mu naught over 4 pi. We have the current of the wire, I, and now we've evaluated the cross product. Okay, we said that dl cross r hat is simply y dx in the z hat direction. Now notice, instead of r squared in the denominator, I have a third r right here. So I should put something like r cubed. Now, of course, I want not the magnetic field due to a tiny piece, but the whole thing. So I need to now integrate. If I integrate from negative L to L, I should now obtain the magnetic field of the entire wire. So I'll call that B wire. And notice I've already pulled the constant out, mu naught over 4 pi. Notice as well that things like y, the position of my field point above the source, the wire, that stays constant. So I can pull that out. And even better, this one's always the nice one. Okay. Notice that z hat is also constant. Right? It points in the same direction in space. So I can pull that out of the integral. Okay. So I have y z hat. And now I have the integral from L to negative L of y divided by, and now I'll plug in the expression for the magnitude of r. I have x squared plus y squared to the 3/2. Take a minute, do the integration. Try your standard techniques. Got it? Well, you say u sub won't work because you don't have a term of x in the numerator. So yeah, you say one of the clues is that this radical in the denominator. Let's try a trig sub. Okay. Oh no, not a trig sub. Yeah, in fact, I think we've already done this trig sub. Yeah. So it's a good review. Let's go at it. We'll have to draw a triangle. Okay. I always draw a triangle just to remind myself of what I'm, which substitutions I'm doing here, where. So I'll just label my triangle like this. Okay. That means that something like, sine of theta is going to be equal to y over r. Okay. And let's see, cosine of theta is going to be equal to x over r. I'm going to go ahead. Let's go ahead and work on this one here. This means that if I take a derivative of both sides, I get something that says negative sine of theta d theta equals, now I got to remember r depends on x and y, so maybe I should get rid of that and put x squared plus y squared to the 1/2. Okay. So I have negative sine of theta d theta. And now if I take the derivative of the right-hand side, I'm going to have something like more space. Let's go ahead and take the derivative of this right-hand side here. So I have something like negative sine of theta d theta. That's the left-hand side. And the right-hand side, well, okay. If I take a derivative of x, I just get 1. So I have something like x squared plus y squared to the negative 1/2. Now I got to take a derivative of the second term. I've got to product rule this. So what do I get? I get plus x times negative 1/2 x squared plus y squared to the negative 3/2 times 2x. Well, keep going. So what do I get here? Well, oh, goody goody. Let's take a look here. The 1/2 cancels the 2. And I'm going to go ahead and find a common denominator. So right here, this I have to write as x squared plus y squared over x squared plus y squared to the 3/2. So notice I multiplied both top and bottom by the term x squared plus y squared. Okay. That adds 1 to the exponent. And then what do I have? Well, don't forget the negative sign, my classic negative sign drop. So there's a minus right there. Okay. So what do we have here? We have x squared, so the x and the x, divided by x squared plus y squared to the 3/2. And now you can see the value of having the common denominator. Oh, goody goody, I have an x squared minus an x squared. So at the end of the day, I have something that says negative sine of theta d theta equals, let's say, y over, now there's a reason why I'm doing this, x squared plus y squared to the 1/2. And then what I have left over is a y divided by x squared plus y squared. But notice this first term, the reason I peeled it off, notice that that is exactly what sine of theta is. This thing that I've underlined here, well, that is sine of theta right there. y divided by r. Oh, goody, goody. That means I can cancel this and cancel that. And I apologize. Good gravy. I'm just not on the ball today. I should have a dx floating around at the end of this thing. There should be a dx floating around, a dx floating around. So where are we at the end of the day? I've run out of space. We have something that says the magnetic field of the wire is equal to mu naught over 4 pi. We have our current. We still have our y. We have our z hat floating out. We have the integral from negative L to L of dx over x squared plus y squared to the 3/2. But now, I will rewrite it. So maybe I shouldn't have pulled this y out. C'est la vie. We go from negative L to L. We have a y over x squared plus y squared to the 1/2 with an additional dx, x squared plus y squared. And this first one, with our trig subs, we called that sine of theta. This one, if we go back and look at our trig subs, I believe that this is just simply negative d theta over y. Right? Let's see here. Dx divided by x squared plus y squared equals negative d theta, and we have to move the y over to the other side. So we have this. Well, goody goody, we're home free now. Keep that I, that z hat there. We have the integral of sine of theta d theta. I'll keep the negative sign in there. And I'll just evaluate the integral and then do the back substitution. That's just my personal preference. Okay. Z hat over 4 pi. Of course, you say, oh, I know that already. That's just cosine. That's cosine of theta. Right? The derivative of cosine gives you negative sine. So we go backwards. And now I'll go ahead and back substitute. I'll undo my trig substitution. And we note we have to go back and look. The cosine is x over x squared plus y squared to the 1/2. Oh, excuse me again. Don't forget that y. This y right there. Sneaky, sneaky. And we evaluate from negative L to positive L. Well, go for it. What do we have? We have B of the wire equals mu naught I over 4 pi. And we evaluate. Well, evaluating at the upper limit gives us something like L over L squared plus y squared to the 1/2 minus a negative L over negative L squared plus y squared to the 1/2. You see the negative, negative, that gives me a positive. And so I have B wire equals, I have two of these, so I have a 2 mu naught I over 4 pi. And then I'll put all of the distances together. we have an L over y, L squared plus y squared to the 1/2 in the z hat direction. Of course, you see the 2 and the 4. We could put a 2 here instead. And there we go. Da 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 da. Here is the magnetic field due to a finite current carrying wire located directly above the center. Pretty cool, huh? Of course, the reason that I did a finite one, you say, Greg, why'd you do a finite one? This makes life difficult, trig subs, yada, yada, yada. Okay. Let's go ahead now. How about an infinite wire? Okay. If you're really close to this wire, really, really close, and what do I mean by close? I mean that y is much, much smaller than L. Okay. So you don't actually have to have a physically infinite wire. As long as you are close to the wire as compared to the wire's length, you can then approximate it as infinite. So let's go ahead. What is the magnetic field due to an infinite wire? So what do? We need to take the limit as L goes to infinity of B wire. And go ahead, take a minute. You probably see it already, but go ahead and pause the video. Okay? You get something that says mu naught I over 2 pi. L runs to infinity, so I've got to keep that one in the numerator. I'm multiplying, okay, so I got to keep that y there. Now right here, inside the square root, because L is large and y is constant, that means that I can ignore the y completely and just get rid of it. Which means that I have L squared square rooted, which means I end up with an L. And of course that z hat still sits there. You say, oh, goody, goody. That's always nice. The L cancels the L. And I am left with something that says, I'll say the magnetic field of an infinite wire is equal to mu naught I divided by 2 pi y z hat. There we go. 2 for the price of 1. Pretty sweet, huh? Thank you for your attention. Keep up the good work, and I'll see you next time.